welcome back to IDIS 343. Now, last time, we introduced the transportation problem and built up a greedy heuristic, a quick kind of common sense rule for pushing product from plants out to warehouses. And that heuristic, hands us a feasible answer fast, but it doesn't promise the cheapest way to ship products from plants to warehouses. Today, though, we will find the optimal, in other words, the best solution. We will basically write the pair tablets problem down as a formal optimization model, parameters, decision variables, constraints, and objective. Then we generalize it, from this one pair example into the compact closed form notation you'd actually use on a real network. Now let's reconsider the example 6.1, the Pair Tablet Corporation. Pair builds tablets in 3 plants, Sunnyvale, Dublin, and Bangkok, and ships them to 4 warehouses, Amarillo, Teaneck, Chicago, and Sioux Falls. Everything's in thousands of units. The plants, make 45, 120, 95. The warehouses need 80, 78, 47, 55. Here's a detail worth pausing on. Add the supply, that's 260. Add the demand at, also 260. Total supply equals total demand. That's a balanced problem, and that's basically why every constraint we write is an equal sign. The last table, by the way, gives the shipping cost per 1,000 units on each route. Now, before we touch pairs numbers, let's name the 4 components of a mathematical programming formulation, in every optimization model. First, parameters, the known quantities, the constants that, describe the problem and don't change while we solve. Second, decision variables, basically the unknowns, the actual choices the model gets to make and we want to find the solutions for. Third, constraints, the rules any acceptable solution has to respect. And fourth, the objective function, the one thing we're trying to make as small or as large as possible. Remember these 4 because every model in this course, no matter how fancy, is really just these same 4 pieces in different formats. All right, parameters first. On the left, you see the 3 plants are plants indexed by IDIS, each with a capacity. Those are a sub I. A sub 1, which is Sunnyvale location, has capacity of 45. A sub 2 is 120. A sub 3 is 95. On the right, the 4 warehouses, our sinks indexed by J, with demand B sub J, demand at warehouse J, 80, 78, 47, 55. And every line linking a plant to a warehouse, carries a unit cost, C sub IJ, meaning the unit cost of shipping products from plant I to warehouse J. For example, C sub 11, Sunnyvale to Amarillo, is 250, while C sub 34 is, a little steep at 1,730. These 12 costs are fixed, we don't change them. They just describe the world we optimize inside of. Now for the part the model actually controls, the decision variables. Look at those arrows. Each one is now, labeled. X sub ij is the amount of products shipped from plant I to warehouse J. So X sub 11 is the flow from Sunnyvale to Amarillo. X sub 12 is Sunnyvale to Teaneck, and on down the line. How many? 3 plants times 4 warehouses, that's M times N, gives basically 12 decision variables. And that little multiplication is, the whole reason big problems get hard fast. 3 by 4 is 12, sure. But 1,000 by 1,000 would be 1,000,000. Hold that thought, it comes back later. All right, here's the whole model in almost plain English using the notation we introduced earlier. This is, before any algebra. Basically, parameters, the A's, B's, and C's. Decision variables, the X sub ij flows. Then 3 families of constraints. 1, shipment out of each plant equals its capacity. 2, shipment into each warehouse satisfies that warehouse's demand. And 3, non-negativity, because you can't ship a negative tablet, plus the objective, minimize total cost. Notice we haven't written a single number yet. This is just the architecture. The next few slides we will use the notation to build the model. Now let's start with the objective. What we're minimizing. Total cost is, just every roots unit cost times how much we send on it, all added up. On screen, you see the full thing, 250x sub 11 plus 420x sub 12 and onward through 1730x sub 34. I won't read all 12 out loud. The pattern is what matters here, right? Each term is basically Cij times Xij, a cost times a flow. Add the 12 together and well, you've got total transportation cost in dollars. That number is what the solver drives down as far as the constraints allow. All right, first family, what flows out of each plant? Take Sunnyvale. Basically everything it ships, x sub 11 plus x sub 12 plus x sub 13 plus x sub 14 adds up to 45. Its full capacity, same idea, for Dublin. Its 4 flows sum to 120 and Bangkok's 4 sum to 95. Now notice these are equal signs, not less than or equal. In an unbalanced problem where we had more capacity than the demand, we'd write less than or equal, well, ship at most what you've got. But pair is balanced and every single unit of capacity has to land somewhere, which forces a strict equality. Now, second group of constraints, what arrives at each warehouse. Amarillo needs 80, and those can come from any of the 3 plants, for example. Well, we add the 3 flows landing there, x sub 1, 1 plus x sub 2, 1 plus x sub 3, 1, and, set that equal to 80. T-next 3 flows add to 78, Chicago's to 47, Sioux Falls to 55. And notice the index pattern, well, just flipped. For capacity, we fixed the plant and summed across warehouses. For demand, basically, we fixed the warehouse and sum across plants. Same 12 variables, just sliced the other way. All right, third group of constraints is the simplest, but skipping it could break everything. Every flow has to be greater than or equal to 0. X sub 11, X sub 12, all the way through X sub 34, all 12 non-negative. Why state something this obvious? Well, the math doesn't know it's obvious. To a solver, a variable can go negative unless you say otherwise, and a negative shipment would basically mean tablets flowing backwards, and worse, it could let the model fake a cost reduction. And that one short line, basically keeps the whole thing honest. Now we start stacking the pieces into one model. Up top, sits the objective. Minimize that 12-term cost sum. Underneath come the capacity constraints, and the slide, well, labels each. Sunnyvale equals 45, Dublin 120, Bangkok 95, each tagged capacity limit. Reading a model this way, top to bottom, is basically exactly how you'd hand it to a colleague. Objective first, then the rules, what we also write it as subject to. And we're halfway there. The demand and non-negativity rules, come next. All right, and here's the bottom half. The 4 demand constraints, Amarillo 80, T-next 78, Chicago 47, Sioux Falls 55, each, tag demand satisfaction. And then the single non-negativity line sweeping in all 12 at once. Count them up, well, 3 capacity rows, 4 demand rows, basically 7 equality constraints, plus the 1 block of non-negativity. Put the halves together and you've got a complete linear program, an LP for short, nothing missing, nothing extra. The next slide, shows it all on one page. And there it is, the entire pair model, objective plus all 8 constraint lines on a single page. This is, the open form. Open form basically means we wrote out every term and every equation by hand. Nothing hidden behind shorthand. For a 3x4 problem, well, that's totally manageable. 12 variables, a handful of rows, you can read it all in one glance. Take a good look now, because the next chunk asks a simple but powerful question, what happens when the problem's way too big to write out like this? Now here's the catch. We could write pair in open form only because it's tiny. 3 sources, 4 sinks. But real networks, aren't tiny. A company might ship from hundreds of plants to thousands of stores. Writing every term by hand, that's hopeless. You'd fill a book and still, make a typo. 12 variables here, 1,000 by 1,000, well, would be 1,000,000. We need to state the same model, without listing every line. That's the closed form, compact generalized description from summation signs and index sets. Same model basically, just in a language that scales. Let's translate each piece. All right, start with the objective. In open form, it was, 12 separate cost times flow terms. In closed form, they all collapse into one line. Minimize these equals the double sum over I from 1 to m, and for each I, sum over j from 1 to n of c sub ij times x sub ij. Read it, well, as a sentence. For every plant I and every warehouse j, take the unit cost, multiply by the flow, and add it all up. One line now, does the work of 12, and basically it doesn't care whether m and n are 3 and 4 or 3,000 and 4,000. The notation, just doesn't grow. Now, capacity next. Open form gave us 3 rows, 1 per plant. Closed form, writes a single template, the sum over j from 1 to n of x sub ij equals a sub I. And that holds for all I in 1 through m. That little for all I is, doing heavy lifting. Basically, stamp out this equation once per plant. Set I to 1, you get Sunnyvale, I to 2, Dublin, I to 3, Bangkok. And that one line generates as many capacity constraints as you have plants. 3 here, 3,000 somewhere else. All right. Demand is, the mirror image of the capacity in one sense. This time we sum over I, the plant scenes from 1 to m, and set it equal to b sub j for all j in 1 through n. Basically fix the warehouse, sweep across every plant feeding it. Set j to 1, you get Amarillo's 80, j to 2, Teaneck, and onward, through all 4. Now notice the symmetry. For capacity we summed over j and indexed by I. Here we sum over I and indexed by j. Same structure, just pointed the other way. Now non-negativity is, the cleanest of the 3. Open form, listed all 12 variables one by one. Closed form, just says x sub ij is greater than or equal to 0 for all I and for all j. Basically, one short line covers every flow in the network. 12 here, 1,000,000 in a giant problem. All force non-negative in a single stroke. And that is really the payoff of index notation. The statement, stays exactly this short, no matter how the problem grows. All right, here's the entire model in closed form, on one tidy page. Minimize the double sum of cost times flow, subject to the capacity template summed over j for all sources I, the demand template summed over E for all sinks j, and, non-negativity for every I and j. Set this beside the open form page from before. Basically, they describe the exact same pair problem, same optimal answer, same everything. The only difference, is how we wrote it down, and only the closed form survives contact with a real industrial size network. Now we've built the model, but the model, just sits there until something solves it. So how do we get the actual optimal plan? 2 steps basically. First, you implement the model in a programming language. Python, C++, C#, Java, Julia. Second, you hand it to a solver, an engine, built to crunch linear programs fast. For a tiny problem like pair, even Excel solver does it in a blink. For industrial scale, you reach for the heavy hitters, CPLEX, Gurobi, GLPK, GAMS. And that closes the loop. We took a messy shipping question, turned it into 4 clean pieces, generalized it, and now we know the path to an optimal answer. That's mathematical modeling works. Thanks and gig 'em.